Good morning, everyone. My name is Bilal Mirza, and today I'm going to talk about sequential extreme learning machines for class imbalance and concept drift. So first, I'm going to define what extreme learning machines are, what is sequential learning, what are class imbalance and concept drift problems in sequential learning. Then I'm going to propose two application-specific methods. One is to tackle class imbalance problem, and the other one tackles both class imbalance and concept drift problem in sequential learning. And then I'm going to propose a generalized method that can work under different environments. So throughout this talk, I'm going to discuss about classification using machine learning. So for those who don't have a background in machine learning, in classification, we have some input patterns, and we're trying to categorize them in one of the given categories or classes. So generally, it has two phases. In the training phase, you are given input patterns along with the associated class labels. You use this information to train machine learning based classifiers such as artificial neural networks or support vector machines. And when the classifier is trained, you use in the testing phase, you're giving unseen input patterns, and then you have to predict which class or category these patterns belong to. So in this work, we have used extreme learning machine as the base classifier. It's a type of artificial neural networks, but in traditional artificial neural networks, the training time is quite long, especially for big data sets. There are two reasons behind it. First is that they use slow gradient descent learning algorithms such as backpropagation, and then all the parameters in the neural network has to be trained iteratively. In extreme learning machines, the training speed can be thousands of times faster than traditional neural networks, and it can obtain better generalization performance. It uses single-step least square error solution for training the neural network. It doesn't require any parameter tuning. The input weights are randomly assigned, and the output weights are determined analytically using this least square error solution. Generally, when you are training a classifier, you are given a complete data sets a priori. But in the domain of data streams, the samples arrive sequentially over time. So if you use standard classifiers such as ELM, it has to be retrained every time new samples arrive with the complete data set. So alternatively, you can use online sequential version of extreme learning machine, which actually stores the previously learned information and update itself only with the newly arrived samples. So that in two ways we can do sequential machine learning, either chunk by chunk or one by one. In chunk by chunk, the data is arriving in the form of chunks, and in one by one or online learning, the data arrives one at a time. So the first problem that we encounter in sequential learning is the class imbalance problem. Traditional classifiers assume that the class distributions are equal. That is, the number of samples in each class are almost the same. But in real-world application, that is not the case. You take the example of medical diagnosis of a rare disease. So the number of subjects having a particular disease, rare disease, is much less compared to the number of subjects without that disease. So if you use a traditional classifier to train such kind of data set, it will be biased towards the majority class. What does that mean? It means that it can always have a very high overall accuracy if it classifies everything belongs to the majority class, even if it ignores the minority class. And in the medical application, minority class is usually the target class or the rare disease. So we cannot apply standard machine learning algorithms in such environment. So the class imbalance learning algorithms consider every individual accuracy and try to maximize this accuracy individually rather than just maximize the overall accuracy. Broadly speaking, the class imbalance learning methods or CIL methods are divided into two groups: external methods or internal methods. In external methods, you actually modify the training data set by either undersampling the majority class by removing some redundant information, or oversampling the minority class by creating synthetic artificial samples. And in the internal methods, you don't modify the training data set, you just modify the learning algorithm, which in the example include cost-sensitive learning, where you assign a higher misclassification cost to the minority class. The second problem that occurs in sequential learning is concept drift problem or non-stationary problem. The statistical characteristics of data streams change over time. The example you can take of the online shopping behavior of customers changes seasonally, or the long-term medical analysis. So the online predictive model should be able to track such changes and adapt accordingly, which raises the so-called stability plasticity dilemma. So you have to balance between the previously acquired information and learn the new information. Now that I've given background about extreme learning machine and sequential learning and the two problems associated with it, I'm going to define some open challenges. The first one is that in sequential learning, there's no method that can tackle class imbalance problem in one-by-one learning mode. Similarly, there is no sequential learning method that can tackle class imbalance and concept drift in one-by-one learning. Then there's a problem with efficient storage for recurring concepts. So in concept drift learning, sometimes the old concepts which are forgotten become relevant again. So we have to store this information in an efficient way. Also, all the previous methods, they only discuss two classes, but in real world application there can be multiple classes, and there can be multiple minority classes, and then there will be multiple classes which are having concept drift problem. Finally, there's no generalized method. There are application specific methods which can tackle class imbalance problem or can tackle concept drift problem, but it's very difficult to predict the nature of the data stream a priori. So we don't have a generalized method that can work under different conditions. So we propose, first we propose two application specific methods. The first one, Wsclm, is actually for tackling class imbalance problem. The second one, Eso Clm, tackles both class imbalance and concept drift problem. And the third one is a generalized method that that automatically select the appropriate learning strategy. It doesn't matter if your data stream is balanced or imbalanced, it is stationary, non-stationary, it is two-class or multi-class. It works under all the conditions. So the first method that I'm going to discuss is called Weighted Online Sequential Extreme Learning Machine, or Wsclm, for binary class imbalance learning. So as I mentioned that in sequential learning, there is no class imbalance problem, class imbalance learning method that can work in one-by-one learning, because the typical solutions include data sampling methods which require a chunk of data instead of one sample at a time learning. And another problem with data sampling method is that in highly imbalanced data streams, the data chunk may not contain any minority class sample. So these methods cannot deal with this situation. Also, for data sampling methods, there is some extra cost of analysis and processing, because you're trying to remove some redundant information. So you have to determine which information is redundant. And then if you're creating artificial minority class samples, you have to perform certain algorithms to create informative samples. So in Wsclm, we first initialize the network using weighted least square solution. So it's, I mean, in traditional extreme learning machine, you use least square estimate solution, and in weighted Wsclm, we use weighted least square solution. So the difference in these two is just this weighting matrix, which actually contains the weight information related to all the samples. So these weights are class specific. What does that mean? It means that every sample is assigned a weight which is inversely proportional to its class size. So it acts as a cost sensitive learning method, because a majority class sample will ultimately be assigned a lower weight compared to a minority class sample. So after performing some mathematical manipulation, we end up in a recursive weighted update equation for Wsclm this way. We evaluated the performance of weighted Wsclm on 15 benchmark imbalance data sets belonging to different domains with different features and different imbalance ratios. So on 13 out of 15 data sets, Wsclm performs better than OTA, which is a state-of-the-art learning methods in class imbalance domain. The second method that we propose is ensemble of subset online sequential extreme learning machine, or Eso Clm.
Bilal, it's Pei. It's fabulous talk, but could you help us with your previous slide? Gave us just a little bit introduction. What are the 15 data sets you used?
Okay, so
because without us understanding better of the data sets, we wouldn't be able to follow your concepts that why some of it fitted better than the other. If
okay.
You can help us out. But it's really nice. I really enjoy your talk.
Thanks. Okay, so these data sets are like benchmark imbalance data sets which are downloaded from UCI repository. So, for example, this PIMA diabetes dataset, it contains samples of patients. Like it has two categories. One category belongs to the subjects which don't have certain diabetic level, and the other category where we have like diabetic level, which is the target class. So this is medical data set. The other one is, for example, this oil data set. It's a oil spill data set. So this data set is acquired from satellite, where you are trying to detect how many oil spill occur in a particular place. So these are the events which are like rare events. You don't see oil spill every now and then. Most of the times there's no oil spill. So that's why this is a typical example of imbalanced data set. So similarly, in diabetes, if you take random subjects, not everyone has diabetes. So this is also an imbalanced data set. Others are this car data set belongs to like car manufacturers which are trying to determine which brand of car is more like popular. So you have like 6 different classes, and not all of them are equal. Some cars are more popular than others. So if you're trying to train a machine learning classifier with this kind of data set, it becomes difficult because of the imbalance problem. Okay, so the next method that I'm going to discuss is Eso Clm, which not only tackles class imbalance problem but also concept drift problem, which is the non-stationary problem. So this method, we have like a main ensemble which takes care of the class imbalance problem. It maintains multiple individual classifiers. Each of them is trained on a balanced subset of the original imbalanced data stream. Then there is a change detector which promptly detects different types of concept drifts. And then there is an ELM store which efficiently leverage prior knowledge of recurrent concepts. So generally there are 2 types of drifts to be detected. One is sudden, the other one is gradual. Sudden drifts are easier to detect because if the performance falls below a certain threshold, you can just remove that particular classifier. But gradual drifts are difficult to detect because the performance degrades gradually, and sometimes it can be mistaken as noise. So we use statistical decision theory, in which we apply hypothesis testing. So let's assume GI is the geometric mean of the current evaluation I, and we calculate conditional probability density function PDFs of GI under a null hypothesis and alternate hypothesis. So we assume Gaussian PDF, and we calculated these PDFs using this formula. and then we apply a likelihood ratio test. So if L is greater than a predefined threshold, it corresponds to an alternative hypothesis, or we can assume that change is detected. But if it's greater than or equal to tau, that means no change is detected. So for this method, we actually use 4 benchmark imbalance datasets which have concept drift. So 3 of them, they are synthetic dataset, and the last one is electricity consumption dataset. So in this dataset, we are trying to actually predict the electricity consumption under different seasons, because it is not a static dataset. The electricity consumption changes seasonally. In summer, it's different. In winter, it's different. So on all the 4 data streams, our method performs better than the state-of-the-art Learn++ method. But the main difference is the number of maximum hypotheses it stores. So for example, you take CR dataset example. Learn++ maintains 1,000 classifiers in the ensemble, while Eso Clm only maintains 18 and still produces better result. So the third method that I'm going to discuss is Metacognitive Online Sequential Extreme Learning Machine, or MOS-ELM. This also tackles class imbalance and concept drift problem, but it's more of a generalized method because it can work under different conditions. I'm going to discuss it later. So the motivation behind proposing this method is that it's very difficult to predict the nature of data stream a priori, because we don't know if the data stream is balanced or stationary. And for example, if we are giving an imbalanced data stream and we know that there is concept drift, we can apply Eso Clm. But what if the data stream is balanced or stationary, or what if it's initially imbalanced and later become balanced? So we don't know if Eso Clm is the ideal method to use in such environments. Also, the previous methods, they only discuss data streams which have only 2 classes. There are no sequential learning methods that can tackle multi-class imbalance problem or multi-class non-stationary problem. So eventually we are looking at a automated or self-regulatory method that can adapt learning according to the changing nature of the data streams. So we use metacognitive learning, which is actually inspired by Nelson and Naren's model of metacognition in humans, which consists of a metacognitive component and a cognitive component. So what does metacognition means? It's one's knowledge concerning one's own cognitive processes or anything related to them. So basically, metacognition controls cognitive process by selecting best learning strategy. So the metacognitive component contains dynamic model of the cognitive component and a self-regulatory mechanism to decide what, when, and how to learn. So metacognitive component compares information in the new samples from the data stream with that of the cognitive component using certain knowledge measures. So these are the knowledge measures that we use. That is, the first one is predicted class label, the second one is a loss function, and the third one is geometric mean, which is a common evaluation measure for imbalanced data streams. So this is our machine learning based metacognitive model. So the cognitive component is just the simple ELM classifier, and in the metacognitive component, we have a latest version of ELM classifier. We have a change detector which keep tracks of the concept drift problem or non-stationary problem. Then based on the predictive class label, error function, and G-mean, which are the knowledge measures, we select a suitable learning strategy from a pool of these strategies. It can be undersampling, oversampling, cost-sensitive weighting, windowing, neuron addition. So these are the available. You can have other type of learning strategies also, but for our application, we restricted ourselves to these particular strategies. So this is basically this metacognitive component controls the learning of standard classifier. We also came up with a unifying equation that works under different conditions, and actually it reduces to certain application specific methods under certain conditions. For example, if your data stream is balanced and stationary, this equation reduces to Osclm. Similarly, if your data stream is imbalanced but stationary distribution, it reduces to our previously proposed Wsclm method. And if the data stream is balanced but it is non-stationary, it reduces to Fosclm method. And finally, if the data stream is imbalanced and it is non-stationary, it doesn't reduces to any previous method, because there is no previous method that can tackle these problems simultaneously. There's no equation for that. So we evaluated the performance of MOS ELM in different conditions. So the first condition is non-stationary with balanced data sets. So we compare our method with the method specific to these application, and on all the four data streams, our method outperformed the previous methods. The second application is imbalanced data set with non-stationary concepts. So here also, so basically these are the same data sets that we used previously. The first three are synthetic data sets, which are frequently used for performance evaluation of like sequential learners, and the last one is electricity consumption database. So here also MOS ELM actually produces better results on almost all the cases except spiral data set, which is gradual drift problem. So for gradual drifts, Eso Clm is generally a better solution because it uses multiple classifier. It's an ensemble based classifier. So these are the graphical representation of the previous results. So there you can see the timestamp. It actually indicates the changing nature of the data stream. So initially the data stream is kind of stable, but suddenly it changes. So that's how, if you see the other methods, it takes time to adapt to the changing environment, but our method actually adapts quite fast. We also evaluated MOS ELM performance on multi-class imbalanced datasets without concept drift, and in most cases the performance gain is significant. And also the multi-class imbalance problem with concept drift is a very new problem, because most of the existing method, they only discuss two classes. So in this example you have multiple classes and all of them are going through change. So for this timestamp it uses these parameters. So later timestamp the parameters changes. So it's kind of a non-stationary environment, and then the number of samples in each classes are also different. So this is a complex situation where you have multiple classes, each class there are multiple minority classes, and each class is suffering from non-stationary problem. So in this kind of environment also, our method produces much better results than the existing methods. So in conclusion, first I identified two main problems in sequential learning: the class imbalance problem and concept drift problem. Then I proposed two application-specific methods. The first one is Wsclm, which tackles the class imbalance problem. The second one was Eso Clm, which tackles class imbalance problem and concept drift problem. But both these methods, they only discuss two class problems. Then the third method is Metacognitive Osclm or MOS ELM, which is a generalized method because it can work with binary class data streams or multi-class data streams. It can work with balanced or imbalanced, stationary or non-stationary data streams. And also we came up with a single Wsclm equation which can tackle class imbalance, concept drift, and the combined problem. So these are the proposed methods and their target application. So as you can see, Wsclm and Eso Clm actually targets one or more of the applications, but most CLM can target all the applications. It can target class imbalance, concept drift, binary class, or multi-class. So these are the journal papers related to the proposed methods. These are some conference papers. Thank you for listening to the talk, and you can ask any question if you want.
It's Pei. At first, I want to thank Bilal, who's actually just arrived a couple of weeks ago and already getting settled around UCLA and also prepared this Friday technical call upon the invitation of Vincent and Colleen. So we thank you very much. And Bilal, at this moment, I think the methodologies you've described definitely have important applications in the clinical data sets that we're currently looking at. I think when you presented using different downloaded data sets to analyze the characteristics of these data sets to see which model it fits, it probably will help us out before we apply to any clinical data sets, that we gave more specific feature definitions of what data sets would fit which model nicely. I also very much like the last slide you have where you kind of summarize what is required to address what type of model. I think the key now is we sit together going through the different variables on the data sets that we have, both for the congestive heart failure models as well as for the MESA models. When we met with people at NHLBI 2 weeks ago, we were also asked to look at the COPD data sets. That data sets has different sub-cohorts. I could also get in contact with them. The lucky sense is that at the same time, NHLBI has invited the pulmonary division at UCLA to join the NHLBI-wide COPD data analysis and cohorts enrollment. So we can also get data sets from the COPD data sets from them. But we need your advice and guidance on carefully defining the features of the data sets. And then we can look at the variables together. David, are you online?
Yeah, I'm online, Pepe. I listened to Bilal's talk. It's very technical, but yeah,
potential applications is enormous, David. So
yeah, I agree.
And look through the data sets carefully and work with Bilal to go through these approaches together.
Yeah, so I will need to sit with Bilal to really carefully look into all these models that he proposed, and then we can.
So David, can I ask a favor? Can I ask you and Bilal meet today?
Yeah.
First, try to understand better. So the test data sets, there are a few of them are medical data sets, David, where Bilal showed. If Bilal can, they are public available. So if Bilal can get these data sets in front of you, then you can get a look at what are the features, properties, and variables of these data sets. Then you will have a better idea what's the difference of these versus the 3 data sets we have.
Yeah,
Okay.
we'll do that.
Yeah.
Okay.
That sounds okay.
Yeah, because I think there are at least 4 of these 15 data sets are medical data sets. Maybe I missed some when you showed that slide online.
Yeah, there are quite a few medical data sets which we use.
Yeah, so David, the key is go through these data sets, look at what they are, what their variables are, what their features are, and then you can compare, because you have some idea of the heart failure data sets as well as the MESA data sets. We haven't got access to the COPD, but we should be able to, because NHLBI has already invited UCLA to join COPD, and part of it came out of the meeting we had with them 2 weeks ago.
Yeah, we can do that. That's
Okay, all right.